Welcome back. In today's video, we will continue to work with the same region and calls for services in ArcMap in the topic measuring geographic distribution. So in this video, we will use how to calculate standard distances, also known as standard deviations, for spatial data. So measuring the compactness of a distribution provides a single value that represents the dispersion of features around the center. This value is calculated by measuring the average distance of the features from the mean center and by how much the individual distances vary from the average distance. This value is called the standard distance deviation, or simply the standard distance. If you're familiar with statistics, you might probably know what the standard deviation and dispersion means. So measuring the standard distance allows you to quantify the amount of dispersion in a set of features. It's calculated by determining the average distance each feature is from the mean center and then determining a value for how much the distance deviates from the average distance. The results are shown on a map as circular rings of 1, 2, or 3 standard deviations, as which the calculation of mean centers and natural geographic component of each feature is used to calculate the standard distance. It is important to note that standard distance circles does not determine grouping or clustering. Only the features are occurring close by. A standard distance circle may include several groupings and clusters. So in this video we'll work, the goal is to show the standard distance for each station. First we'll calculate the standard distance circle both with and first without weighting and second with weighting, and our weight field is F as you might remember. So this is my map. This is my battalion area, let's say, and we will work with this area. This is my alarm territories. Color it differently, and these are my active stations, and these are my proposed stations. So we can turn off the proposed station, and these are the calls for services for February 15. So let's search the standard distance. It's in spatial statistics. So this is a standard distance. Let's have a glance, fast glance. Measure the degree to which features are concentrated or dispersed around the geometric mean center. So these are the inputs, in our case calls, and this is the output. So bigger the circle, it gives a circle. So bigger the circle, bigger the dispersion and standard deviation. So calls, circle size is let's say there's standard distance, distance just so far without weight. Case field is station. So let's click OK. So see that we have the circles. As an output we have a polygon consisting from circle features, and some are the bigger ones, circles, and some are the smaller ones. These are the 4 stations. So we have shape area, center X, center Y, standard distance C. This is one for station 1, etc. We can just zoom. So this has the bigger standard distance and therefore the bigger the dispersion. So, and we repeat the step, but this time we will add also weights. So we are concerned with standard distance weights. We are also concerned with the importance of a date. So as a weight, as you might remember, we will this FII. We can just again open and see that calls doesn't have the same weight. FEE, so 10 is the highest weight, 8 is smaller, and 1 is the zero weight, which is cancelled calls. 10 is a danger to human health, human life. The highest priority, the smallest priority is false calls, and the moderate priority is damage to physical property. So we will now create standard distance based on the importance of a call as well. So let's click OK. So we can change the color here. I mean the outline color to distinguish. Let's make it yellow. When we included the weight factor, we can see that there is a difference between when we measured the standard weight with the without the weight factor, which is the purple color, and with the weight factor, which is a yellow color. See that there is no significant difference, but for station 1 there is a significant difference. When we included the weight factor, the size of the previous circle is much bigger, and the second one is smaller, which means that in this case weight factor played a significant role. So in this case it's more compacted comparing to the unweighted standard distance. So station 1 and 14 here shows a more compact standard distance circle when the weight factor is included. Overall, the compactness of the standard distance circles for all the stations is better when the incident priority code is added as a weight to the analysis. So in some cases, some incidents, some calls fall within the circle. Most of them fall within the circle, but sometimes they are outside of the circle. So features outside affect the size of the circle and thus the compactness of the distribution. With the weight field applied, the features outside the circle might not affect the calculation in a negative way if their weight value is low. In most cases, you saw that adding a weight reduces the size of the circle, and yes, in most cases. It is important to note that features that might belong to different geographic clusters still have a single circle to represent the distribution. Once again, the standard distance circles show compactness of the overall distribution, but do not show the grouping or clusters. So what kind of other real-world examples might be used? For instance, let's imagine that the police department may measure the compactness of a set of crime data to determine a possible patrol area. A concentrated area can be easy to patrol with extra officers, while the dispersed area may not highlight a clear tactic. Or in many other instances as well, real life examples.